Dear students, in this video we are going to discuss energy of simple harmonic oscillator. Here we will do the classical treatment when body moves between maximum and minimum position about the central or equilibrium position, then how its energy varies between maximum and minimum. So here we will consider a block of mass m attached with the spring, and here we consider that, let's suppose this one is the equilibrium position and we represent the equilibrium position with x is equal to 0. It is also called as central position or equilibrium position. So let's suppose this is the maximum position in the positive x direction and this one is the maximum position and in the negative x direction. Okay, now this block, when we stretch or compress the spring, this block will oscillate between these 2 points, between maximum and minimum x. So when block oscillates between these 2 points, then it has some kind of energy, and this energy will also oscillate. As the block oscillates, then energy will oscillate between these 2 positions. Then here I will tell you that this is a kind of simple harmonic motion and how energy varies between maximum and minimum. So this is the kind of classical representation of simple harmonic oscillator. And let's suppose here we consider that when the block is at t is equal to 0, then initial SI, let's suppose that this is the maximum amplitude. This is the amplitude, maximum position from mean position in any direction, either it is in the negative x direction or it is in the positive x direction. It is called as amplitude. So at x is equal to, when A, it means then when the block is at its maximum position, at that time velocity is 0. Okay, so in classical physics we consider that this is the representation of simple harmonic oscillator, that is the block attached with the spring. So its total energy, what will be its total energy? Total energy of this harmonic oscillator can be represented as it is the sum of kinetic energy plus potential energy. So that total energy is also called as the mechanical energy of the system. It will be the sum of kinetic energy and potential energy. Now here we will define what is the kinetic energy and what will be the potential energy of this simple harmonic oscillator. So first I will write an equation to know that the kinetic energy is equal to 1 by 2 mv square. Okay, but we also know that in the case of simple harmonic motion, we can represent the simple harmonic motion by x equal to a cos of omega t plus phi. Okay, and then you know that the velocity is equal to, so when x is equal to a cos of omega t plus phi, then velocity is equal to dx by dt, and you know that the velocity will be equal to minus omega a sine of omega t plus phi. Okay, so we can write the equation for kinetic energy. You know that kinetic energy is equal to 1 by 2 mv square. It will be equal to, when we put the value of v, this will be equal to 1 by 2 m omega square a square into sine square omega t plus 5. Okay, now this is your equation for kinetic energy of simple harmonic oscillator. Okay, the kinetic energy. So now you know that the potential energy is always equal to potential energy is 1 by 2 kx square. Whenever the body attached with the spring, then kinetic energy can be written in 1 by 2 kx square. Now again we know that x is equal to 1 by 2 a cos of omega t plus phi. When we put the value of x, the potential energy will be equal to 1 by 2 k. I can write it like k a square cos square omega t plus phi. Okay, now next I can uh, rewrite the kinetic energy in the form of k square and a square instead of omega square. And you know that for this purpose I need to make some replacement, and you know that omega square is equal to k divided by m. When I put the value of omega square is equal to k by m in the velocity in the kinetic energy equation, then kinetic energy will be equal to, so I can rewrite the kinetic energy equation. Kinetic energy is equal to 1 by 2 m omega square a square into sine square omega t plus phi. So by putting the value of omega, it should be equal to, kinetic energy will be equal to 1 by 2 into k a square into sine square omega t plus phi. Okay, now I can write the equation for total energy of simple harmonic oscillator. So I can write the equation for total energy can be represented by E, the sum of kinetic energy plus potential energy. So here I will put the value of kinetic energy and potential energy, which will be equals to 1 by 2 k a square into sine square omega t plus phi plus 1 by 2 k a square cos square omega t plus phi. So it will be equals to 1 by 2 k a square can be taken as a common factor, then remaining terms will be equal to sine square into omega t plus phi plus cos square omega t plus phi. From trigonometry, we know that sine square theta plus cos square theta is always equals to 1. So using this trigonometric relation, then our total energy equation will be equals to 1 by 2 k a square into 1. This will be equals to 1 by 2 k a square, because cos sine square omega t plus phi plus sine square omega t plus phi will be equals to 1. So from this equation you can see that our total energy, which is also called as the mechanical energy of system, is proportional to the amplitude square or square of amplitude. So it means that if k is large, then alternatively it means that when kinetic energy is large, then potential energy is small. Okay, and alternatively we can say that when potential energy is large, then in that case kinetic energy will be small. Okay, so because the total mechanical energy varies between the kinetic energy and potential energy. So whenever x is at maximum position or at maximum amplitude, we can say that plus minus a, then in that case v will be equal to 0. That is, here I can redraw it like this one. Okay, so this is x is equal to 0, and here this one is the maximum amplitude of this block of mass m in the positive x direction, and this one is in the negative x direction. So this one is the maximum amplitude. So whenever x body is at, our block is at x is plus minus a. So at that position, the velocity is equal to 0. So it means that at this position, the total energy is the total mechanical energy will be potential energy 1 by 2 k a square. And alternatively, when we say that when body is at mean position, x is equal to 0, in that case, we know that the total v will be the maximum. No, v is not 0. No, velocity is the maximum when body is at x is equal to 0. So in that case, the kinetic energy will be equal to 1 by 2 m v square. And so I can say that 1 by 2 m omega square, I can write it as m omega square into a square, and by putting the value of omega 1 by 2 m into k over m into a square, again the total mechanical energy, which is the kinetic energy, this will be equal to 1 by 2 k a square. So at mean position, the total mechanical energy is in the form of kinetic energy, and at extreme position at x is equal to plus a, or either it is x is equal to minus a, the total energy is in the form of potential energy. So at equilibrium in position, we can say that total energy is equals to kinetic energy, and at maximum position it is potential energy. Okay, now we will go to the graphical representation for the full cycle of the motion. Now I can plot the kinetic energy and potential energy as a function of time. So here kinetic energy and potential energy as a function of time. So the kinetic energy, I can write the plot for kinetic energy like it will be, I can start it from here, it will be like this one. So this line represents the kinetic energy. Okay, and then for potential energy, I can say that it is like this one. So this is the graphical representation of potential energy. So from here you can see that this is the time and this is the potential and kinetic energy. So this graph, from this graph you can see that whenever the potential energy is maximum, then at the same instant, then kinetic energy will be minimum. So here, when the kinetic energy is maximum, then potential energy is minimum. So it means that total energy varies between the kinetic energy and potential energy. So in the same way, I can plot kinetic energy and potential energy as a function of distance. This was as a function of time. So this was the time t by 2 and 0. Now I can plot the graph as a function of position. So as a function of position, I can write it like this is the potential energy and kinetic energy, and this one is the position. As position varies between between the maximum amplitude in the negative x direction, and then we have the 0 position, that is the equilibrium position, and then we have positive A in the positive x direction, the maximum amplitude in the positive x direction. So first I can write that, for example, for the kinetic energy, for the kinetic energy, you can say your graph will be like this one. That is, at mean position, your kinetic energy is maximum. But alternatively, when you plot for, this is your for plot for kinetic energy. But when you plot for the potential energy, your potential energy will be opposite to the kinetic energy, and it will be like this one. This is your plot for potential energy. Here you can see that the potential, the curve of or the plot of kinetic energy and potential energy versus displacement. Okay, energy, here you can see that energy is continuously being transferred between the kinetic energy and potential energy. When you reach at the maximum position at amplitude, here you can see that these are the maximum position. So here the kinetic energy is zero, but potential energy is maximum at this position. So, but at equilibrium position, the kinetic energy is maximum, but potential energy is zero. So this graph tells us the variation of kinetic energy between kinetic energy and potential energy. So we can write the equations like we know that total energy is the sum of kinetic energy and potential energy K plus U. So I can write it like 1 by 2 mv square plus 1 by 2 k x square. So and the total energy is equal to 1 by 2 k a square. So from here V will be equals to, I can write the V will be equals to k over m into a square minus x square under root. Okay, or in other words, I can write the equation for this one. V will be equals to k over m equal to omega square, so I can write it plus minus omega into a square minus x square. So this is the velocity varies between plus minus like this one. Okay, and then you know that the maximum acceleration varies between plus minus omega square a. So now I will go to the figure which represents the full cycle of the motion for the kinetic energy and the potential energy. So here this figure representing the full cycle of the motion for kinetic energy and potential energy. So here we suppose that initially the block is at time t is equal to 0. At time t is equal to 0, the block is at its maximum position in the positive x direction, which is equal to plus a. Okay, when block is at here, then at maximum position, the velocity will always be equal to 0. And when velocity is equal to 0, then in that case the acceleration a will be equal to minus omega square a. I have already told you that acceleration varies as plus minus omega square a. The acceleration is, as you know, that it is towards the mean position in the negative x direction, it's equals to minus omega square a. So whenever at the maximum position, then in that case the kinetic energy will be equal to 0. So here the total mechanical energy will appear as total kinetic potential energy, which is equal to 1 by 2 k a square. Now we go to at time, let's suppose at time t by 4. At time t by 4, when block is at position x is equal to 0 at equilibrium position. So at time t by 4, when position x is equal to 0, when x is equal to 0, then here again the velocity is in the negative x direction. So this will be equals to minus omega a. And acceleration here will be equal to 0, and now total mechanical energy appears in the form of kinetic energy, because in the equilibrium position the total energy is kinetic energy and potential energy will be equal to 0. As I have already written the equation for velocity, you know that velocity is equal to plus minus omega into a square minus x square. Okay, so when at another time, let's suppose at this position, we suppose this is time t by 2. At time t by 2, when the spring is compressed, now it is at amplitude, the negative acceleration at maximum amplitude minus a. So here its position is minus a, and but acceleration will be in the towards the equilibrium position, and at that at maximum position either it is the positive amplitude or in the negative acceleration, where minus a it always be equal to 0, and its acceleration now in this case is towards the equilibrium position and is accelerating towards the positive acceleration. So in that case the acceleration is omega square a. So here the kinetic energy at maximum position is always equal to 0. Again, the total energy, mechanical energy, appears as a function of potential energy, will be equal to 1 by 2 a square. Now this was the time t by 2. Now at another time, let 3t by 4. Okay, at this time, when time is 3t by 4, at this time, let's suppose body is again, now from here it's moving again towards the equilibrium position at x is equal to 0. Now here the velocity is in the positive x direction, it will be equal to plus omega a. At x is equal to 0, it will be equal to plus omega a from this equation. Okay, and acceleration here again at equilibrium position it will be equal to 0, and total energy appears as a kinetic energy and potential energy. Now at time t, that is at full cycle, here it started from x is equal to a, and now it again clock is at position x is equal to a. So at full cycle again I say that position is at x is equal to a, again velocity will be equal to 0. Now the acceleration is again directed towards the equilibrium position, the negative acceleration will be equal to minus omega square a. Kinetic energy is equal to 0, and total mechanical energy appear as a function of potential energy. So this was the variation of the kinetic energy and potential energy for the full cycle between plus A and minus A. Here you can see from this table that potential energy and kinetic energy varies alternatively between maximum and minimum position, and this is the variations with the time. Okay, now we will go to some examples of simple harmonic oscillator type motions. Okay, now let's suppose that here I will take the most common example. Let the motion of molecules. If we have the motion of molecule in solid, okay, or atom in the solids, motion of atoms or molecules in solid. As we know that, let's suppose we have some atoms, like we have this one atoms, and here the binding forces. There are the binding forces within the molecules which are holding the different atoms or molecules together within the solid. Okay, and let's suppose there is the binding force. Again, there is the force. At the end of this force, we have an atom, and let's suppose this is like this one, and I can represent it like this one, So we can say that in the case of solids, the forces holding the atoms together are just like the spring. So these are just like the springs, and atoms so can move a small displacement about their equilibrium position. So alternatively, I can represent it graphically like this one. So the graphical representation of potential energy is like this one for the motion of molecules within the solid. The other example which includes in which we can use the idea of the simple harmonic oscillators are like the tuning of television station. In in that case, we can use the idea of simple harmonic oscillator and other observing the laser light emitted by the laser. So all these are examples or ideas in which we can choose the idea of simple harmonic oscillators. Thanks for watching. For more videos, please subscribe our channel.